Today, we're going to talk about parallel circuits. In a parallel circuit, you have several resistors that are each connected to a battery, each in its own separate loop. As you see here down on the bottom, we have a battery, and then we have one loop here with a resistor, and then we have a separate loop that goes around like this with another resistor on it. On the right here, we have another one. Here's the battery. You have one loop and a second loop, and each of these loops has one resistor in it. In order to analyze this, we first need to talk about something called the junction rule. And this is a very simple rule that says for any point in the circuit, the current that goes into this point in the circuit is the same as the amount of current that goes out of the circuit. So for example, if we have this point over here, we could say if 3 amps goes into this point, then 3 amps has to go out. When we had talked about simple circuits and series circuits, this rule was kind of implied, and it gave us the information that everywhere in the loop the current was the same. We're just making it a little more explicit because we're going to have multiple paths now. Here's an application of that. Let's say we have a wire over here, and it's got 3 amps going into it, and it reaches this point right there, and there's a junction there. It's a splitting path. And on one of the paths we have 2 amps going down. Then this junction rule tells us that coming out of this path we have to have 1 amp. So that we have 3 amps going in, and then we'll have 3 amps going out of that point. It's a pretty simple rule, and it's pretty powerful for analyzing circuits. Here's another example. Here we have a 4-way junction. There's one point in the center that has 4 wires going in or out of it. All right, if we look at it, we see that 3 of the wires have currents defined on them. We have 5 amps over here, we have 2 amps over here, and 3 amps over here. Given the information that we have, we can see that we have a total of 7 amps going into this circuit, and then we've got 3 amps coming out, and then we have 1 undefined. And if we want the amount of current to go in to equal the amount going out, then we figure fairly simply, I hope, that we have to have 4 amps coming out. So we have 7 amps in and 7 amps going out. All right, this is going to help us to analyze a parallel circuit. Here's an example of a parallel circuit. We have a 12-volt battery up here. We have 1, 2, 3 resistors that are all in parallel. If you look at these situations closely, you'll notice that each of these resistors is in its own separate path around in a loop here. Now, what we did with the series circuits is we said, all right, let's start with the battery. Here, this battery is producing a 12-volt potential difference. So if we call the side over here 0 volts, then the higher voltage side has to be 12 volts. And every point on the circuit that's connected by just a wire to one of these known points has the same voltage. You can just sort of go down the line on each side and define the voltages. Next, we can look, for example, at this space here between the right and the left going through that resistor. And when we do that, we say, aha, going across that resistor, there has to be a change of 12 volts. And there's 3 ohms in that resistor, so that allows us to figure out that there must be a current going in this direction from the high voltage to the low voltage of 4 amps. We can then go to the next one, and we can say, this guy over here, we've got 12 volts of potential difference, the same as in the other resistor, but this guy's got a 6 ohm resistance. So that tells us that there's going to be a current going this way of 2 amps across that resistor. Then we can go down to the third one and say, this guy also has 12 volts potential difference. You'll notice that each of the 3 resistors all had 12 volts of potential difference, and This guy has 6 ohms again, so it's going to have 2 amps that goes through it, going from high voltage to low voltage. All right, super. We figured out the currents through each individual resistor. Now let's trace what happens to those currents as we go through these various junctions. We go over here on the right, we can see that we have to have 2 amps going down here so that we have a total of 2 amps going through this whole path here. We have to have 2 amps. So this is going to be 2 amps going up like that. And now on the right side, we have an intersection right here. And we see we have 2 amps going to the left, and we have 2 amps going down. So here, we have to have 4 amps of current. And if we do this on the right side and look at on the left side and look at this junction, we have 2 amps going up into it and 2 amps going left into it. So we have to have 4 amps going up. All right. Now we look at the next junction. We'll start. Let's do this guy right here. We see we have 4 amps going down and we have 4 amps going to the left. So we have to have a total of 8 amps going down into that junction. And similarly over here, we have 4 amps going up and 4 amps going left into it. So we have to have 8 amps going up. So we can see that in this circuit, we have a total of 8 amps coming out of the battery. And then it splits off. First 4 amps goes to the one side, and then 2 amps goes to the next one, and then 2 amps goes to the next one, and so on. All right. Now, in the series circuit, we thought about what we call equivalent resistance. And if we look at this circuit from that view, if we try to collapse the whole parallel circuit down into a single resistor, we can do that again. We have a 12 volt battery with 8 amps of current running through it. And so we can do R equals V over I is equal to 12 volts over 8 amps. We get that the total resistance of this seems to be about 1.5 ohms, which is actually smaller than any of the individual resistors. We had 2 6 ohm resistors and a 3 ohm resistor, and somehow we ended up with a total resistance in this being only 1.5 ohms, much smaller than the individual resistors. That's because we had multiple different paths, and having the multiple different paths made it easier for current to flow around this loop, where in a series circuit we had multiple different blockages on the same path, which made it harder. Let's do one more. All right, we do this one here. We've got a 24 volt battery, and here we've got 0 volts around this side, because this is the side with the smaller bar on the battery symbol. We got 24 volts, 24 volts, 24, and 24. We can work out the current through each one. We see that the current goes this way, and we have 24 volt potential difference between here and here. And so we say there has to be 6 amps going that way. And then this one, we have a 6 ohm resistor and a 24 volt voltage difference. So we say there's got to be a current going this way of 4 amps. And then on the third one, we have 12 ohms of resistance. So we're going to have 2 amps of current. We follow this 2 amps up this way, and we got 2 amps and 4 amps going into it. So we have 6 amps going up here, and then we've got 6 amps going in and 6 amps going up. So we have 12 amps going up this way. We can follow this same logic here, down on the other side. We have 2 amps going down, so we have 2 amps coming out and 2 amps going to the right. So we have 6 amps here, and then 6 amps going down, 6 amps going to the right. So we have 12 amps there. So we have a battery here with 12 amps going into and out of it for this circuit. And we can consider the equivalent resistance of this, just like we did in the previous one. We can say R equals V over I. R equals 24 volts over 12 amps equals 2 ohms. And again, with a parallel circuit, we get less resistance than the individual resistors would have suggested. All right. Now, when we want to calculate equivalent resistance, we have a kind of a complicated formula that we use for parallel circuits, and it's got a little bit of a pitfall in it. In series circuits, we added up the individual resistances to get the total resistance. In a parallel circuit, we add up 1 over the resistance of each resistor to get 1 over the total resistance. I'm going to show you how that works here. Let's start with our first one. We had a 3 ohm resistor and two 6 ohm resistors. We want to add these together. We get 2 over 6 plus 1 over 6 plus 1 over 6 is 4 over 6, is 1 over the equivalent resistance. Now, I've seen several students get stuck here and say, aha, the equivalent resistance is 2/3. But that's not quite right. The reason it's not quite right is you have to flip this over and you get 3 over 2, or 1.5 ohms. And if we remember, going way back up here, this was in fact the exact thing that we saw for this circuit when we calculated it. Let's go back and try the other one. We had a 4 ohm, a 6 ohm, and a 12 ohm resistor. So we try to calculate the equivalent resistance. We go, aha, 3 over 12 plus 2 over 12 plus 1 over 12 equals 6 over 12. We get a half. Is the answer a half? No. We have 1 over Req is a half. So the equivalent resistance is 2 ohms. We go back up to the top, look at this guy that we calculated, and wouldn't you know it, we got 2 ohms there. Ta-da. All right, so this equivalent resistance formula gives us a way to calculate the total resistance of the circuit. It has this pitfall, though, where you have to remember this step here of going from 1 over Req to Req. All right, in summary, we have 3 rules for parallel circuits. The first rule is that the voltage across each individual resistor, V1, V2, V3, etc., is the same as the voltage coming out of the battery. The second rule is that the current that comes out of the battery is equal to the sum of the individual currents going through each individual resistor. Here we don't have one loop with the same current everywhere. We have several different loops, and the total coming out of the battery is the sum of the amount going through each individual loop. And then finally we have this special equivalent resistance formula with 1 over Req equaling the sum of 1 over each individual resistor. And that's about it for parallel circuits.